Hello viewers, in this video I will discuss about the application of Gauss law. In this application of Gauss law we are going to find the electric field due to uniform infinite charged sheet. Okay, so we are going to find the electric field due to a infinite charge sheet. See, uniformly charged. So at a point P, okay, so kept at distance x. So we're going to find the electric field due to this charged sheet, that too you see that infinite, see like this. So here I am having a charged sheet, okay, but here we are going to find the electric field to infinite. See, if it length goes like this, here it goes like this. So for an infinite plane sheet, if I have a point P here, what is the value of electric field? That we have to find it, okay. So you know we have a formula, you know that E is equal to Q by 4 pi epsilon naught R square. Whether we could use this formula? No, because this is the formula for a single point charge. But here we have many charges in which they are uniformly spaced. Okay. So next, whether you could use continuous charge distribution formula. Okay, we can also do by that. For this we see that we have to choose pairs in which the contribution for each pairs we have to calculate and the resultant electric field we have to calculate. This could be done for a small portion. For infinite plane sheet, this will become a very complex thing. So to help us to solve this problem, we are getting the help from Gauss law. Okay, so to use the Gauss law, first we have to choose a Gaussian surface. Okay, so we have to choose a Gaussian surface which is required to find the electric field. Okay. Here I am having a point B. So first of all, here we have to choose a Gaussian surface. Okay, so for infinite plane sheet, what surface we have to we can choose for the Gaussian surface? See, here I am going to a rectangular parallel piped. Okay, or it could be a cylindrical surface, or it could be a cylindrical surface. So whatever may be. Okay. So in early lecture we have seen for an infinite long wire with a cylindrical surface. So for a different thing, we can choose a rectangular parallelepiped for this particular application. Okay. So now we're going to choose a rectangular parallelepiped as a Gaussian surface for this infinite charge sheet. Okay. Okay. Okay, more or less it is okay. So we have chosen, we have placed this infinite plane sheet inside a Gaussian surface. We have chosen a Gaussian surface. See that this Gaussian surface. So we have this particular direction x. We are going to find the electric field at point P. So it is equal. See, but the electric field will be in both the directions for a plane sheet. See, electric field will be in both these directions. See, in both the directions. So if I consider a point P at distance x, we can also consider equal spaced in this direction also as x. Okay, because the electric field will be flowing in both the directions. So here we are considering this electric field as parallel to the x-axis and we are omitting the components in y and z axis based on this kind of arrangement. We are taking only the electric field parallel to the x-axis. Okay, so fine. So we have chosen the Gaussian surface. Now next step is we have to find the electric flux. Okay, due to this Gaussian surface. Okay, we see that the electric field direction is like this. So we have we choose the surfaces. So here we have one, and here also we will be having a surface 2. Okay, so this is a surface 2 facing in this direction, and 3 and 4 downward direction. See, like this. So this is a rectangular parallelepiped, because the rectangular parallelepiped means all the 6 faces are rectangle. That is the condition. See here, surface 1, okay, then surface 2, then this direction and this direction. So we have to find the electric flux in both all the 4 directions. Okay. So the total flux will be flux due to 1, due to 2, due to 3, and also due to 4. So we have to find the flux due to each surfaces. So if I have 1, see, if I consider a small area vector dA here. I missed the pen. So if I have chosen a small area vector dA here, see, the area vector will be pointing in outward direction for a 3D object. Okay. So here we see the electric field is parallel to this surface. Okay. So we are taking closed integral of EDA, and what is the angle between the area vector and the electric field? Here it is cos 0 degree, because both are in the same parallel direction, it is 0. So similarly phi 2. Here also it is closed integral. See here this direction. If you take a small area element dA, it will be pointing in the outward direction. Here also the electric field is parallel to the area vector. Okay. So here we have EDA cos 0. Okay. Similarly, we are moving to phi 3. See, we have area vector here. The area vector will be pointing in the outward direction. And the angle between the electric field and the area vector is 90 degree. Here it is 90 degree. So here close integral of EDA cos 90 degree. Okay, so similarly we are moving up to 4. Here also see in downward direction. So here this is also dA in downward direction. So close integral of EDA cos 90 degree. So from here we can see the cos 90 is 0. So these two components will get eliminated. Okay, so only remaining here is only your phi 1 and phi 2. Only the components in the x direction. This and this one. Okay, so the total flux will be phi 1 and phi 2 only. Okay, so cos 0 it is 1. So here we are having, this is close integral of EDA plus close integral of EDA. So this will be E and close integral of dA plus E and close integral, because E is constant here, only the dA varies. So the dA, nothing but the close integral of dA, nothing but the area of the rectangular parallelepiped, that is A. So EA plus EA. So the total flux of the Gaussian surface. So the total flux of the Gaussian surface. Total flux of the Gaussian surface, we are getting it as 2EA. So you get the total flux as 2EA. Now from Gauss law you know that the flux will be equal to charge by epsilon, or 1 by epsilon times the value of charge. So what is the charge here? See here, for this uniform charge sheet we have the surface charge density. Here we have surface charge density sigma. That is, sigma is equal to charge per unit area. Charge per unit area. So the charge here is, so the charge here it is Q is equal to sigma into area. Okay, fine. So now from Gauss law you know that the total flux will be equal to charge by epsilon naught. Okay. So what we have found, the charge total flux we found it as 2EA. So 2EA, which is equal to, what is the charge we have found it? It is sigma A. Sigma A by epsilon naught. Okay. So from this AA gets cancelled. From this we are getting the electric field as sigma by 2 epsilon naught. Okay. So this is the value of electric field we have got. by choosing this Gaussian surface. This is the value of electric field due to this infinite long plane sheet, plane sheet, uniformly charged plane sheet. See, the beauty is, see, the electric field does not depend on the distance x. It only depends on the charge sigma value. It is independent of the distance for this particular infinite charged plane sheet. And we see that this expression is more true and more valid for in the middle portion of the infinite charged plane sheet, middle portion. Okay, so that is the signs given. Okay, so this is the expression to find the electric field is infinite charged plane sheet. So what if it is a cylindrical surface? Okay, so we can also see with respect to cylindrical surface. So most people will be having the doubt. So what if you are choosing a cylindrical surface? See, like this, a cylindrical Gaussian surface. If I have chosen a cylindrical Gaussian surface and we have an infinite charge sheet inside. Okay, see, the electric field will be flowing in this particular direction and also in this particular direction. So if I have chosen this as 1, 2 and upper as 3 and lower as 4, we will be getting the same as we have chosen rectangular parabola also. See, for 1 the area vector will be in this direction, for 2 area vector will be in this direction. Only these two will contribute. 3 and 4 the area vector will be in perpendicular direction to the electric field. So it will get cancelled. So here also we are getting the 1 and 2 as 2EA. See, but at the end of the formula here we see that it does not depend upon the area of the Gaussian surface. So whatever may be the Gaussian surface, that value is not included in your electric field formula. So whatever may be the Gaussian surface, both are true. Both are true for the case of a infinite charged plane sheet. Okay. So if you choose cylindrical surface also, you will be getting the same formula only. Okay. Thank you.